Greetings and welcome to the video on chi-square. And there are a couple of different types of chi-squares, but we're going to talk about the chi-square goodness of fit. So let's talk about chi-square goodness of fit. Okay, so the chi-square is the Greek letter here is the chi symbol, and we just can denote it with the chi-square in this particular fashion. It was introduced by Carl Pearson right around 1900. Carl Pearson was a British mathematician and kind of one of the founding fathers, if you will, of the field of statistics in general. And you'll remember that name from the Pearson product moment correlation that we did in earlier modules in this class. Now, the interesting thing that we have been using data in our inferential statistics that have been, well, let's just kind of draw one in. So let's just go back to this general design where you've got an X, an O, an R, no treatment, you've got a control here. Another observation. Well, let's just say what you're going to get is you're going to get a mean here of the group 1, you're going to get a mean here of group 2. Well, this data that we're collecting has been continuous data, and on the either interval or ratio scale, measurement scale. If you don't recall what your variable types were, continuous and discrete, and your measurement scales, nominal, ordinal, interval, ratio, I would encourage you to go back and review that information. But everything we've done in inferential statistics up to this point in time has been using kind of these continuous types of variables. And now what happens if you have nominal data? Can you still infer something from a nominal variable in a sample and infer it to the population? And the answer is yes, you can, and it's one of the ways to do it is with a chi-square goodness of fit test. So you're going to use it with nominal data. And what are we going to really be using with nominal data here is counts, right? Counts or frequencies of items or events. This will become more intuitive as we go along here. So often you want to take a sample from the population of nominal scale data, and then you want to infer whether the population from which it came conforms to a specified theoretical kind of distribution. So hello, let's pull this back up here. So for example, let's talk about a simple coin toss. Let's say here that our data come from (100) actual coin tosses with a fair coin. Not unnecessarily unbalanced or anything in terms of the coin. The null hypothesis that we want to test here is that data come from population having a 1-to-1 ratio of heads to tails. Now you can change this. It doesn't always have to be a 1-to-1 ratio. What's the alternative hypothesis here? Data do not come from, or do not fit, and my writing is going to pot here, do not come from this population. When I say come from this population, what I'm talking about is it does not fit that theoretical distribution. That's why it's called goodness of fit. So let's just kind of set this scenario up here. So let's say here's the category. We're going to say we have a heads event, a tails event, and let's set up a little table here. I think we can draw that line a little bit better here. Let's see. Okay, we're going to put the N here. All right, so let's get some things defined here real quick. Let's call the frequency, this f sub I, the observed counts, what you're observing in your actual sample from your population, and you want to compare that to f hat sub I, which is going to be, this is your expected or theoretical ratio that you're going to compare it against. Expected counts. Okay, so let's just get our f I and our f hat sub I. Okay, so we said it was a 1-to-1 ratio, and we did 100 actual coin tosses. So if our n is 100 and it's a 1-to-1 ratio, that means we would expect 50 heads and we would expect 50 tails. Remember, the f hat is what we're expecting, and we're expecting a 1-to-1 ratio. Okay, and let's just say that we actually got, say, 62 heads and 38 tails. The question is this distribution of 62 to 38 far enough away from this 1-to-1 distribution that we can say this is significantly different from this 1-to-1 ratio? So the general formula, general calculation for this test, so chi squared equals, we want to sum through I equals 1 through the k levels, and we'll talk about this in just a second, of the fi minus f hat I squared divided by, didn't give myself enough room there. So what is this saying? This is taking, well, what is, let's do this so we can bring out in blue. Here's blue, and we'll say expected is red, and red. So what are we doing here? We're saying we're taking the observed minus the expected, squaring that, and dividing by expected. And we're going to do that for each ith level all the way through all k levels. Okay, so how many k levels do we have here? Well, here's the first one, here's the second one. So in this particular one, k equals 2. Okay, we had, actually I did that wrong. We have, here's 1, heads, tails 2. K still equals 2. I just put the 1 and the 2 in the wrong spot. I guess you have two possible outcomes here, heads and tails. You can extend the goodness to fit to k equals 3, k equals 4, k equals 5. I'll come back to that in just a minute. So what does this mean for us? So we want to take 62, which was our observed for heads, minus what we expected for heads, which was 50, square it, divide it by expected, which was 50, and then to that sum, because we have to do this sum function here, 38 minus 50 squared divided by 50. This equals 2.88 plus 2.88 equals 5.76. So chi-squared equals 5.76. Now, similar to our general steps, this is calculated chi-square, and we're going to have to compare it to a critical chi-square value, which is going to be chi-squared at a certain alpha and a certain nu or degrees of freedom, and for us that means chi-squared at 0.05, and degrees of freedom here, nu, so degrees of freedom equals nu equals k minus 1. K is our levels. We had two different levels, right, heads and tails. So 2 minus 1 equals 1. So degrees of freedom equals 1. So 1. So we have to go find out what this value is. What is it? Well, we look it up in a chi-square table. Guess we'll leave it up here. So if you look, here's our rejection region right here, and we're saying this distribution of heads to tails, if we want to challenge it, it has to be on this side of our cutoff region. And where do we find that? Well, here's degrees of freedom, or our new column here, and we read down this column. Well, we only had one, and then our alpha level is here, and so 3.841 is our actual value. So our critical chi-squared was 3.841. We set up the inequality where we say 5.76. This was calculated, was greater than 3.841, which was critical. And so we're going to challenge the null and reject it. And we're going to say that the data did not come from this population. Okay, so that's basically the nuts and bolts of the chi-square goodness of fit. Now you can extend this to more levels, so and to other things. So if we took a sample from the population, I'm just going to overwrite on some of this stuff, but we took a sample from the population, instead of heads and tails, we wanted to say what was the distribution of men and women. We could also say something like what was, we could extend this to, you could say Democrats, Republicans, and independents. So instead of going from k equals 2, in this particular instance we'd have k equals 3 different groups, and you could go, just keep these different rows going. What that means is when you're calculating your degrees of freedom over here for critical for your critical chi-square, you just have to adjust accordingly, and as you can see, your degrees of freedom can go up. It can really go up to infinity, depending on how many levels that you have. So again, just wanted to introduce at least one test in this class that had to do with nominal data, and you're basically trying to decide whether or not what you have observed and the frequency counts of what you observed are different than what you would expect, and then you have to define what your expectation is, because it doesn't have to be one-to-one. You could change if you knew that the men were 40% of the population and women were 60%. Whoops, you could change, let me get this back up here. You could change this here from a 1-to-1, you could change it to a 60-40 and just say, is your observed counts meet that expected count breakdown of 60-40. So two things that can happen here: you can expand k, and you can change what the expectation is of the distribution of the ratio of these different k levels. So again, just an introduction. Wanted to make sure you had just another tool in the tool belt. That's it for this video. Thanks for watching.